Welcome all to our joint presentation. My name is Madeleine and my co-presenter Sheja is Sheja. Our talk today is titled Treatment of Missing Data in Bayesian Structural Learning, a simulation study for social science, a case study of antimicrobial resistance. Before outlining our plan for this talk, it's important to note here and throughout both presentations, we are concerned with the field of Bayesian analysis, which is Bayesian belief network applications, here also referred to as BBNs. I will begin this discussion by demonstrating three ways in which social science applications might apply this method. I will then narrow it in and introduce their application within a specific field, that of antimicrobial drug resistance. And as part of this, I'll demonstrate its applicability to this type of approach of thinking in the field before giving a brief overview of a review I conducted to assess the scope of these BBN applications, the use of these BBN applications in the field. My co-presenter will build on these findings, specifically issues related to missing data. She will introduce missing data and the three missing mechanisms, and she'll give a brief review of how BBNs can be used for dealing with missing data. She will then demonstrate a simulation study which compares the performance of two popular approaches for dealing with missing data. And finally, she'll conclude with an application to real AMR or antimicrobial resistance data. Let us begin. In social science, BBNs are typically used in three ways: for variable inference, parameter inference, and structure learning. In variable inference, there is a given structure and set of probability tables. Then, given new evidence or an observation in the network, you can infer the state of another variable in the network. Here, if we observe C to be yellow, given the probabilities of these events, we can infer A is likely orange. In parameter inference, it is the case where from a given structure, you use either data, expert knowledge, or other evidence to define the conditional probabilities or parameters of a network. In other words, it is the process of identifying the probabilistic relationship between variables, here indicated by the question marks. And finally, there's the use of structure learning. This is about understanding the relationships between variables for a given set of data. You can identify the structure of the network through the use of learning algorithms, here indicated by the various arrows. Oh, I've gone backwards. I apologize. I'm just going to use the clicker. Bayesian belief networks also contain useful and actionable motifs which guide social science inference, interpretation, and further investigations. The BBN structures, whether learned or not, capture direct effects, confounders, mediators, and intercausal effects in an intuitive graphical representation. Here I'll describe how, gone the wrong way again, the forks and chains present in these models are understood and useful for social science. In social science, we are often concerned with whether something is a confounder, that is a variable that influences both, typically both of the two variables, causing a spurious association to be seen between them, or a mediator variable, that is a variable that explains the process through which two variables are related. Confounding within BBNs is typically presented by a fork, and mediators are represented by nodes within a chain of arcs. Using these models, let us consider the variable representation represented by the red node. The red node is seen to have a confounding effect on the relationship between the green and blue nodes, indicating that it needs to be controlled for when we're drawing relationships between these two nodes, which representing various variables in the model. However, the same node, when we're considering it as a chain in this diagram, we can see that it is the flow it is in the flow of probabilistic influence between the orange and blue nodes. Hence, it should be controlled. It should not be controlled if the relationships between orange and blue nodes need to be drawn. The intuitive depiction of variables means BBNs make a useful tool for understanding biosocially complex phenomena. I will now explore this further in the case of antimicrobial resistance. What is antimicrobial resistance? Well, antimicrobial resistance, or AMR, occurs when organisms acquire the ability to evade or survive treatment. Resistance is a complicated issue, which is driven by the exposure at insufficient levels of these microorganisms to antimicrobials. Of particular importance to this field is the exposure to antibiotics. Resistant genes can either be inherited or through a process called vertical gene transfer, or in some cases can be shared between organisms and species through horizontal gene transfer. Resistance not only occurs in humans, but in animals and the environment too. Furthermore, these interdependencies are not merely biologically complex, but also intertwine with social factors, making AMR a biosocially complex phenomenon. Bayesian belief networks are useful for dealing with data with complex dependencies. However, there is still a limited uptake of their use in AMR. For some reason, my slide has got the pictures out of date with the bullet points, but there you have them. The premise of Bayes' theory is that initial beliefs can be updated based on new evidence. So imagine this example where you're treating a patient with a certain antibiotic. Your belief in the success of the treatment is high, as this is a typical line of treatment. A prevalence study is carried out in your area and you learn that the prevalence of resistance to your treatment is high. This prompts you to update your beliefs about the probability of treatment success. This initial belief of treatment success is known as the prior probability. When your beliefs are updated by the new evidence, the prevalence study, these new beliefs of the likelihood are called posterior probabilities and are represented here in the equation. Given its applicability to the field, we would expect to see a much more frequent use of this application in the literature. However, as I will present in the review, I found very few applications to this field. The review used an iterative scoping approach. First, the literature landscape was surveyed with a series of initial searches of Google Scholar, PubMed using the terms listed. Then the research questions were developed and centered on understanding how and what areas of research these applications had been applied. Analyses which did not contain Bayesian belief networks, i.e. those that were specifically related to just Bayesian statistical applications, were excluded. Papers were then identified through additional Boolean searches, which were developed from a process called pearl growing, which is a method wherein you use terms and keywords that are identified from relevant papers to inform further searches. And in addition to this, citation tracking was also undertaken. And that's where you look for relevant citations from within relevant papers. Here's a brief summary of the results from this iterative methodological review of applications of BBNs to the field of AMR. This is a table of how and what BBN applications in the field of AMR and antibiotic. And this is a table of how and what of the BBN applications in the field of AMR and antibiotic use. BBNs were developed either as a method to investigate random variable associations, in other words, as like an analysis tool, or for some reason my slides, there we go, as an analysis tool, or used to inform, used as a decision tool, or in some instances as both. All tools were typically for clinical settings, while the majority of analyses were related to meat production. Two notable exceptions include Trenny et al., who considered UTI patients, and Sethi et al., who did both an analysis and developed a tool. A typical concern whether a tool or analysis was being performed was whether was what data was used to inform it, and indeed whether the data included missing observations. The application in this review can be divided into those that used structured learning and those that did not. Of the ones that did not, they used expert knowledge, factor analysis, and other maximization strategies to overcome missing data and fill in the gaps in the network and perform analyses. But for the structured learning, where the data is essential to build the models, these methods were not viable. Instead, the review of these papers suggested three approaches. Papers either did just not mention data concerns, maybe this is because of the type of data they were using didn't typically contain missing data, or they attempted to use only data for which this was a minimal problem, i.e. a small percentage of missing observations, or through the application of other statistical procedures to compute the missing data. How one deals with missing data is an important and vital step to ensuring the computational power of these results, as well as to prevent bias in these analyses. This concludes my section of the talk, and I thank you for your attention. And I now turn over to my co-presenter, Sheja, who will demonstrate another alternative method not considered in the above reviewed articles to handling missing data. Thank you.
Hello, everyone. I'm Sheja. Just to follow up my colleague Madeline, I'm going to talk about missing data and a case study on AMR data. Compared with other fields of studies, missing data are more pervasive in social science research. There are plentiful causes of missing data. For example, unanswered questions in questionnaires. People sometimes refuse to answer some questions because they feel insecure or embarrassed. Missing data not only reduce overall statistical power and precision, but can lead to biased inferences in subsequent data analysis. So dealing with missing data is quite important for social scientific data analysis. Based on the reasons of why values are missing, there are three missing mechanisms. Missing completely at random. The missingness is unrelated to unobserved and observed responses. Missing at random. Missingness is unrelated to unobserved response, but related to observed response. And missing not at random. Missingness is related to both unobserved and observed response. For example, in a study of blood pressure in old people, some values are missing because the machine doesn't work. This is missing completely at random. Missing completely at random cases are rare in reality because everything happens for a reason. If an old man has mobility issues, so he cannot come to the clinic and his issue has been recorded, then this is missing at random, because this missingness is related to a value that we already know. Both missing completely at random and missing at random are ignorable missingness because they are not dependent on missing values. But missing not at random is more tricky. It implies the reason of missingness is dependent on the missing value itself. For example, an old man who suffers from hypertension cannot go to the clinic for checking his blood pressure. The missing value itself reveals why it is missing, and you cannot infer it from the other observed values, so it is difficult to detect. Currently, the vast majority of the literature on learning Bayesian networks rests on the assumption that data is complete. Most conventional software cannot work with incomplete data. We know that learning Bayesian networks roughly consist of two parts, structured learning and parameter learning. Structured learning consists in finding the DAG that encodes dependent structure of the data and maximizing the probability of the graph given data for some alternative approximations. For example, structural expectation-maximization algorithm that we will talk later, and a variational Bayesian expectation-maximization algorithm. It approximates BIC scores and the marginal likelihood. Parameter learning from incomplete data is relatively easier because there is a given no fixed structure. Generally, these approaches assume the missing data are missing completely at random or missing at random, like data augmentation, EM algorithm, bound and collapse algorithm, a robust Bayesian net estimator, and some simple imputation methods. In our simulation study, we compared the performance of structural expectation maximization algorithm and a popular imputation technique, multiple imputation by chain equation. Firstly, we will talk about SEM algorithm. SEM algorithm is proposed by Friedman in last century. When there is a given incomplete dataset, it firstly generates a random network structure and then computes the expected sufficient statistics to complete data. This is so-called expectation step. Then at maximization step, it makes use of the complete dataset to search for a Bayesian network structure that maximizes the expected score function. Any combination of heuristic search techniques and scoring functions can be adapted at this step. These steps are iterated until the convergence is made so that it can find an optimal structure from the incomplete data. The main advantages of SEM algorithm are it searches for the best Bayesian network structure within EM iterations. It finds better structure after each iteration, and it doesn't make assumptions on missing mechanisms. Multiple imputation by chain equation is a popular approach for imputing missing values in social science data analysis. Here is a brief overview of how it works. Firstly, given an incomplete dataset, we impute all values by using univariate imputation methods. For example, here is using the median. Then from left to right, we remove the imputed values from variable A and create a model. For example, a linear regression model using the complete samples, and then impute the values in variable A using this model and other values in B and C. We do this one by one until we get a complete data. Then we use the first imputed dataset to minus the second imputed dataset to get the difference matrix. In order to make the difference close to zero, we iterate the whole process until a predefined threshold is met. We can create several copies of the original incomplete dataset. Each copy can be processed in iterations. Then we can choose to analyze all the complete dataset together or combine the statistical results of each complete dataset. Compared to single imputation, multiple imputation improves the accuracy by factoring other variables in the data to make better predictions about the potential true value of a missing value. And that is why MICE assumes that the data is missing at random. In our simulation study, we compared the performance of these two approaches. Firstly, we generate a random graph with variables from 2 to 20. This random graph is also referred as the original structure in the final step for comparison. Then we sample data points from the random graph to get the complete data. For each graph, we sampled 1,000, 5,000, and 10,000 data points. And then we introduce missing values to the complete data. We set missing proportion from 0.1 to 0.6 at intervals of 0.1. Then we learn the Bayesian network structures either from all complete cases from the dataset completed by MICE algorithm or using SEM. Finally, we compare the learned Bayesian network structures with the original structure, and each condition is repeated 100 times. Here is the example of comparison. Considering their equivalence classes, we compare the skeletons of their structures. From left to right, the first one is the original Bayesian network that is also worked as the reference network. The blue arcs are false negatives and the red arcs are false positives. This is part of our comparison result when there are 1,000 data points. We used precision and recall to evaluate their performance. We grouped the number of variables into 6 categories, and for each category and each missing proportion, we applied one-way ANOVA and two-case honestly significance difference tests. The plot shows when there are missing not at random data, and when the missing proportion is 0.6. Both MICE and SEM approach have better performance than doing nothing, and SEM algorithm has the best performance in revealing the original structure. This conclusion is also consistent in 5,000 and 10,000 data points. Here we compare the difference of these 3 methods, mean of recall, under each missing mechanism when there are 1,000 data points. Each row panel represents each missing mechanism, and column panels represent missing proportions. The y-axis represents the difference of the record mean, which is averaged over the 100 simulations. And the x-axis represents the number of variables from 2 to 20. This plot shows that the outperformance of SEM algorithm increases with number of variables and with missing proportions. We further compared the performance of each method across 3 levels of data points, where there are missing log and random data and the missing proportion is 0.6. It indicates that high number of data points would increase each method's performance, especially when there is high proportion of missing data. We also compared the difference of 3 methods' record means across 3 levels of data points. It indicates that when we increase the number of data points to 5,000 and 10,000, the outperformance of SEM algorithm and the MICE approach over doing nothing won't be as obvious as when there are 1,000 data points. So we can get some conclusion from this simulation study. So both SEM algorithm and MICE approach improves the completeness of Bayesian network structure learned from incomplete dataset. And in some circumstances, for example, when data have high missing proportion and high number of variables, the performance of SEM algorithm is better than MICE. And when there are low number of data points, the outperformance of SEM over the other 2 methods increase with the increasing number of variables and missing proportion. The outperformance of SEM and MICE over doing nothing will decrease when there are a high number of data points. So overall, SEM algorithm shows great promise in dealing with missing data, especially dealing with missing log and random data. So we apply this approach to the real antimicrobial resistance data. The AMR antimicrobial resistance data is collected in Hatua project. This project aims to address antimicrobial resistance in urinary tract infection in East Africa. There are 3 countries, including Kenya, Tanzania, and Uganda. This research aims to identify the drivers of antimicrobial resistance and explore the relationships between these drivers. We extracted 13 variables from the big, complex interdisciplinary dataset. These variables include the identities of patients, like their age, gender, and their treatment-seeking behaviors, like whether they took antibiotics when they had symptoms, and some microbiology data collected from the lab analysis of their urine samples. All these variables are categorical variables, and the number of levels ranges from 2 to 4. Based on the lab data collected from antimicrobial susceptibility testings, we generate a new variable MDR, which is multiple drug resistance. It is antimicrobial resistance shown by a species of microorganism to at least one antimicrobial drug in 3 or more antimicrobial categories. We used the 26 clinical and laboratory standards institutes and M45 protocols for setting cutoffs for different bacterial species and lists of antibiotics. Here, most variables have less than 10% missing values, and the variable MDR has about 12% missing values. This plot shows the missing patterns of this dataset. Not many variables are missing together. This is because we checked them and recoded some missing values if we know why they are missing. There are 1,067 complete cases, which is roughly half of the dataset. We learned the structure from complete cases and applied SEM algorithm to the antimicrobial resistance data. This is the comparison between these 2 networks. The red arcs are additionally found by SEM algorithm, and the blue arcs are additionally found by complete cases. If we take a look at the red arcs, we can see that the arcs additionally found by SEM are more biologically reasonable, especially the arcs between bacterial genus and gram reaction, and the arc between genus and multiple drug resistance. This is also consistent with the findings from our simulation study. That is, SEM algorithm can better reveal the true structure from incomplete data. As we are more interested in the drivers of multiple drug resistance, we can find there are other 6 variables associated with MDR, including the genus of bacteria that infected patients, the type of bacteria, whether it's gram-positive or negative, the gender of patients, the patient's age, and whether patients have been provided the prescription of antibiotics from doctors, and also the hospital level that patients have been to for seeking treatments. This is still an ongoing work, but this provides us a basic idea so we can further explore and look into the relationships between these factors, like why the hospital level that patients have been to is associated with whether patients have been provided the prescription of antibiotics from doctors. We could possibly explore the related policies behind this link. We would like to acknowledge our supervisor, Dr. Anne Smith, Dr. Catherine Keenan, the Hatua data team, St. Andrews University, and our founders that have made this presentation possible. So that's the end of our presentation. Thanks for your attention. Please feel free to ask if you have any questions. And also be great if you could provide us some suggestions on advice. Thank you.